Thanks very much, everyone, for coming along to this distinguished visitor seminar. My name is Mohammed Jawad Abdawadi, and I am a PhD student at QUT and a member of ACEMS and CDS. And it's a great pleasure to introduce our speaker for today, Dr. Rebecca Killick. So Rebecca is an associate professor in statistics at Lancaster University, UK. Their research is in solving real-world problems for data whose statistical properties vary over time. By developing statistical methodologies for change point detection and locally stationary modeling. Killick's research is a feedback loop inspired by problems in real-world applications, creating solutions to those problems and then feeding those solutions back into the problem domain. Killick is co-editor-in-chief of the Journal of Statistical Software, a member of the ROpenSci Statistical Software Peer Review Advisory Committee, and the European Network for Business and Industrial Statistics 2019, Young Statistician for the year. So in today's seminar, Rebecca will present tackling global issues change. So before I hand it over to Rebecca, just a little bit of housekeeping. So Rebecca will present for 40 to 45 minutes or so. And after that, we will have some questions. So you can type your questions into the Q&A function in Zoom as seminar proceeds. And after that, Rebecca can address those questions at the end of the seminar. So the floor is yours, Rebecca. Thanks very much.
Yeah. Thanks, Mohammed, and thank you very much for the invitation today. As I kind of noted as we were coming in, it's still dark here, but it's dark for you at the opposite end of the day. So I'm not a morning person, so please bear with me if I'm a little slow. I've only just woken up. So I'm going to talk to you today about tackling global issues and talking about change. As Mohammed kind of detailed, in my research, every single piece of methodology that I develop has been motivated by a real world application. So I'm hoping today to kind of cover the last 10 years of challenges that I've kind of tackled in the changepoint world from a very high level, kind of giving you a little bit of intuition around why it's a problem and the type of solution that we've kind of created. At the very end of my slides, I've got links to all of the actual papers that I've spoken about today, which is quite a long list, but hopefully I'll kind of give you a flavour of the type of issues that we're dealing with. Then towards the end of the talk, I'll kind of give you some open problems. So I wanted to kind of start just by going backwards a very long way in statistics, where, you know, we're kind of talking about how we started creating model development. So it kind of started around when we were looking at some data and having to start to fit models to data and thinking about the different types of models that we might want to fit. So we kind of all started off thinking, well, what is the mean of a set of data that we're looking at? So you might fit kind of a flat mean line here. Then we kind of realized that that often data doesn't kind of fit this flat mean line, and we started getting trend data coming through, and we kind of think, well, that mean value is not really appropriate there, so let's develop some methodology so that we can actually fit a trend line to our data. Okay, then that was all right for a while, and then we kind of started to get more complicated patterns, some kind of seasonal effects going on here, and we started thinking, oh, well, maybe we should make it a little bit more sophisticated, so we don't just have a trend line, we've got some kind of seasonal factor going on. As we get more and more data these days, we're monitoring processes over longer periods of time, and the sorts of data that we start to get now are looking a little bit more like this. These are artificial examples, but I'll show you some real examples later on. And so the question that kind of change point detection as a field is trying to answer is, how do we model data that's like this? It's clearly not going to just be a small adaptation of the existing methodology that we have for trend or model estimation in this framework. And so we're kind of looking at the whole field is thinking about problems like this, where you might get sudden changes in the statistical properties as we kind of observe the data over an ordered paradigm. So that's kind of the general topic and types of data that I'm going to be looking at today. So as I kind of said, I'm going to give you a little bit of tour of some of the big problems that I've kind of looked at over the last 10 years. We're going to be looking about speed and accuracy, autocorrelation, model choice, and multivariate data. And then I'm also going to detail some open problems, which you'll kind of note that some of these open problems are also the same problems that I've been trying to solve over the last 10 years. We're still not quite there. But we've also got additional problems such as sensitivity to data and also online inference that are starting to become more prominent in the field. So just to kind of be a little bit more concrete about what I mean by change points, the very general definition is that if we have some ordered data, I'm not going to have any equations other than the maths that's on the slide here, so don't worry if you're from another field. But we're just going to have some ordered data here where I'm going to call it y1 to yn. And if a change point exists, all it means is that the statistical properties up until a certain time point tau, and after that time point tau, are different in some way. Okay. And so we've got three examples here. The top one has a change in mean, where you've got a flat mean value, and then at certain points, which we're going to call change points, that flat mean value changes to another level. The middle one is a change in variance. So here we're not looking at the mean change here, but rather the variability within the data is changing. So you've got a small amount of variability at the beginning, then you've got a larger amount, a medium amount, and then an even larger amount towards the end. And then the final one at the bottom is a trend change, where again you focus more on the mean, the kind of the expectation of the data, where you've got a potentially linear, potentially non-linear trend. And again, at certain time points, the coefficients for that trend line will vary. So the problem and the way that I think about this problem is around the fact that if we have one of these sets of data, the easiest way that we can kind of break the assumption of stationarity, so as in the model that we fit to the data is the coefficients of that model are fixed over time. The way that we can kind of break that assumption, the simplest way is just to piece these models together. And so essentially change point detection is about just piecing together the traditional models that we all know and love and have kind of grown up with. We're just piecing those together at the change point locations. So for example, if I just took the first 100 data points here, we would very easily know how to fit a model to that data. It's just a flat mean. Same thing if we just had 100 to 450 here, we know exactly how to deal with that model because we just, again, fit a flat mean. And the way that I get the model for the whole data there is just literally adding up the model 1, model 2, model 3, model 4. And you may be thinking, you know, there's connections here with mixture modeling. Essentially, one way that you could model this is a mixture model, but the mixture weights would vary over time here. And the mixture weight would be, you know, 1 for model 1 at the beginning, 0 for all the other models, 1 for model 2 in the middle, 0 everywhere else, 1 for model 3 at the appropriate point, 0 everywhere else. You could think of it like that if you're used to working with that sort of data. But the easiest way to think about it is literally just 0 to 100. I have this mean, 100 to 250. I have the mean in model 2, and the way that I get the model for the whole data is just to add up the individual models with indicator variables to say if I'm at time point this, that's the model that I'm working on. So that's great if we know where the change points are. So if we know where the change points are, that's a really easy problem to solve. Okay, we can just do that using standard regression techniques with an indicator variable. Okay, the problem comes when I don't know how many change points there are, or if there are even any change points in my data, and I don't know where they are either. So that's the kind of the crux of the problem with change point detection, is we don't know where these change points are. And so if we don't know where they are or how many there are, then that then becomes a problem where we need to identify a parameter, which is the number of change points, and parameters where we're looking at where the change point locations are. And that's when it becomes challenging, because there are 2 to the n-1 possible solutions in a data set of length n. Okay. So this is kind of the problem that we're tackling in change point detection. So if you're thinking about this 2 to the n-1 complexity, that can grow very, very fast as n grows. Okay, and so that then kind of arises to this, well, do I want a fast solution, or do I want an accurate solution? Just like we have in a lot of other areas of statistics. Do I want, you know, the most accurate approach, or do I want something that I can compute in a reasonable period of time? So back in 2010, when I started looking at this problem, the order of the exact solution was n squared. Okay, we could get a solution in n squared. I didn't know it at the time because I hadn't found the paper. It was one of those interesting phenomenon where just as you're about to submit a paper, you do another literature research and you actually find a paper that's done half of your paper, which I was very frustrated about as a PhD student at the time. But luckily, Paul Fernhead managed to calm me down and basically say, no, we've still got a paper here. It's still going to be good. You're all right. So it was order n squared at the time, although as I said, I wasn't aware of that paper when we started this project. And then it was order n log n if you wanted an approximate solution. So you can kind of see that there's a huge difference between the n squared and the n log n there. Okay. So the order n squared solution, what it did is it basically did a dynamic program optimization over the possible change point number and change point locations. What it does is it bookkeeps the location, so it considers the data in a sequential manner and just bookkeeps where the last change point location is. So if we go back to this, you're kind of at the beginning of the data. As you start to roll through kind of the data, you go past model 1 and into model 2, and then you only need to know where the last change point was, which in this case would be at 100. As I go further through the data and I get into model 3, I can then say, okay, well, my last change point was at 250. And then to find all the change points prior to that, I just go back to when I was at 250 and say, well, at 250, where was the last change prior to 250? Okay. And so this is great, but it's order n squared because you're still having to check every potential previous change point location. The intuition that we brought to this was that, well, if you've gone past a change point time, then the last change point is not really likely to be before that. And so if you've had an obvious change point within the data, what's the point in checking lots of, potentially thousands or millions of time points prior to that for seeing if that was the last location of a change? Okay, so that's kind of the intuition behind it. So what we kind of mean by a significant change point, as in a change that is large enough for us to get rid of everything prior to that, is kind of detailed in the paper. But essentially, you've kind of got in this diagram here, if we're at capital time T in our algorithm, and we have a potential change point location S, note that I'm kind of not putting that as a at the optimal time, because it doesn't have to be at the optimal time. But if the change point potential last change point time at S is large enough, then we don't need to check little t, which is much prior to that. Okay, so if we have lots of these obvious change points as we go through the data, then we can prune. We call this a pruning step, getting rid of all of the little t's there. We can prune those options, and that will give us an order n algorithm. Okay. And so the key to getting that order n algorithm is that you get change points or large enough potential change points throughout the data on a regular basis, so that you can basically keep that list of things that you need to check very small. So in reality, you know, there are lots of situations where regular doesn't necessarily have to mean regular through the data, but essentially the longest period you don't have a change point is likely to be the largest amount of time that you have to check within that. So what we showed here is on the left, you've got computational time. The red is the order n squared algorithm that was before, and then the blue is our Pelt algorithm that kind of has a drastic reduction in speed and is kind of linear in time there. But that means that we've got a fast algorithm that is also accurate. So this is an exact solution to the optimization problem of fitting those change point, both the number and the location of the change point parameters. So if you kind of think about this from a standard model building point of view, this is the equivalent of doing an exact maximum likelihood estimation versus, for example, an approximate optim search inside R, where you're kind of optimizing just by iterating through some potential solutions. So that's kind of the equivalent here. So what Pelt gives is the equivalent of an exact maximum likelihood estimation, as opposed to the approximate solution, which is more like the optim search, where you're just trying different parameters and seeing what is a better solution. So on the right there, that's our mean square error for one example, where you can see the blue line at the bottom again is the Pelt algorithm, which is the exact solution. And then the orange and the red are two versions of an approximate solution for the same problem. So as the length of the data increases, you can see that we're starting to get a larger gap between the precise solution given by Pelt and then the approximate solutions that are on the market already. Okay. So this paper, the Pelt algorithm, has software available in the changepoint package in R, and it's been very, very successful over the last few years. A lot of people have kind of been, I think, thinking that kind of it's really helped my career. It's helped me kind of get on the map in that sense. And it means that a lot of people are using this. So for example, NASA uses this inside their spacewalks for checking the pressure inside the spacesuits for the astronauts. We've got it used in lots of different areas of science. So there's been lots of science and nature papers that have used this type of algorithm before, as well as the multitude of other applications that we've got in areas of business and other areas. So now I've kind of given you a reassurance that we can actually find these solutions both in a fast and exact way. Let's look at some more complicated changes here. So the top plot there is one where you can probably look at that and you can probably say, well, I can see that there's a change in the data there. I can see that the left part of the graph clearly has different statistical dynamics to the right part of the graph. Okay. What is harder to ascertain is where that change point is and if there's only one of them. Okay. So there's actually, just like in the other graphs, there's actually 3 change points within that data. And that's just a pure change in autocorrelation process. Okay. But when we're talking about autocorrelation, it becomes a lot harder to determine where the change point locations are. The bottom plot there, again, is a slightly more complicated example where we also have a change in trend line going on. So that's seasonal data, whereby you have both a change in the amplitude. So you can see on the left of the graph, the cycles are happening more slowly than on the right of the graph. If you kind of fix the middle, you can see there's kind of 3 peaks to the right, whereas there's only 2 to the left. And you can also see that kind of that first peak has very little variability in it, whereas as we move through the data, there's more variability. What is also harder to see is that there's actually a change in autocorrelation there as well. So it's not just a variance change going on here, it's an autocorrelation change. But because you've got lots of other things going on, it's really hard to see that by eye. So let's try and think about autocorrelation a bit more. So if you've got autocorrelation within your data, it can be very hard to identify changes having that background correlation process going on. So here's an example of some stock data. This is eBay stock. You can clearly see that it's autocorrelated because of the kind of the up-down patterns and the kind of runs that you get within the data. But there's a clear, obvious change point here. I don't think anybody's going to argue with me saying that kind of around mid-2015, there's a huge change point in the mean of the process. But what's not clear is whether any of these are the smaller jumps that we see just before 2016 or halfway through 2016 are actually change points as well. So the big one that we see in the middle is where eBay announced that eBay and PayPal will be splitting. So that created a huge shock and created a change in mean in the stock price. But was there other stuff going on within this data? It's really hard to see because the autocorrelation will create runs of periods where you have higher or lower values in the data, and you're not sure, is that just due to the autocorrelation in the data, or is that something that is actually a meaningful change? Okay. So one way that we kind of looked at this was we looked for a change in mean with a general, potentially non-stationary second order structure going on. So that means that the background process could potentially be quite complicated, having really long dependencies in a lag structure. I'm not going to say long memory, but kind of getting towards that kind of long memory process in the background. And these were the changes that we found. So we found that the one just prior to 2016 was just due to the changing autocorrelation in the data, which we weren't interested in here. Whereas the one in the mid 2016, that was indicative of an actual change point. We also found one just after the start of 2015, kind of in the run up to the split between eBay and PayPal. So there were some different changes that were made just after 2015 that kind of attributed to that change, if you want to go into attribution in this sense. Okay. But the key thing here is that you just have this background autocorrelation process alongside a flat mean structure. Okay. So now we're talking about kind of correlation and autocorrelation within data. Let's look at some what I would call more natural correlation. So this is an environmental process. And you can clearly see that there's some kind of changing dynamics going on here. I kind of see it as a little bit of you've got a trend process going on towards the end of the data where you've got a clear upward kind of trend dynamic, but then you can also see changes in autocorrelation because the beginning of the data is more highly variable with kind of more up-down processes going on, whereas towards the end of the data, you don't see that as much as you do at the start of the data. So the interesting thing here is we can kind of get into, well, it looks like there might be some autocorrelation going on. It looks like there's potentially some changes going on. There may be trends in some parts of the data, but what type of like underlying model assumption should I make for the individual segments that we're looking at? So what's clear here to me, at least, is that I shouldn't be looking just at a flat mean model as we did in this data here. We should be looking for having a trend as a minimum. Okay, but it's not clear to me whether there is some seasonality within the data, whether the autocorrelation is there, or whether it's just a variance changing within the different segments. Are there any actual flat mean structures in here? It's not really clear to me. Okay, and the crucial thing in change point detection is that where you find the changes is kind of predicated on the assumptions that you're making within the individual segments. So, for example, if I assumed a kind of a flat mean structure here, that trend line is going to be estimated by a series of kind of flat jumps. Okay. That's not desirable because that's obviously saying that there's more changes in the data to get you kind of get a staircase approach to estimate that trend. That's not what's there. Okay, to me, that looks like it's more of a trend line going on. So this kind of arose to the question, how do we actually choose what model is appropriate? Now, when we're looking at this type of data, I actually have thousands of time series at various points across the globe. So I can't look at every single one of these time series and decide what type of model structure is appropriate. Some areas in the globe were better handled by just a flat mean, some had trends in, some had autocorrelation, some didn't, some had no change points at all. So we had a paper in the Journal of Climate where we looked at, well, how can we actually decide between all of these different models in an efficient way for all of these locations across the globe without having to look at every single one individually. So what we did is we had a bank of potential model solutions, so potential models that might fit some of the data. And essentially we used a likelihood principle to decide which of those models might be appropriate. Just like you might do in a manual sense when you're doing linear regression, you put in a bunch of covariates and you kind of maybe do forwards selection or backwards selection to decide which ones are going to be appropriate. It's kind of a similar sort of thinking here, but now we're not just kind of adding and removing or estimating if coefficients are zero. We've got more change point dynamics going in. So it's not that if you add a trend, then that's nested within the previous change point model that was just a flat mean. So there's a little bit more going on there. So this kind of arose because one of my collaborators, Claudie Bellew, who's now at Santa Cruz, kind of wanted to answer the question, is there a hiatus in temperatures across the globe? So there's a bit of a debate in the climate change community around just after 2000, kind of the data that we've got from 2000 to 2020 was kind of looking a little bit flat. So if you look at towards the end of the data, if you ignore that top peak, which is the final data point that came in just before we published, if you ignore that top peak, then there's a potential argument there that there's a flattening out and that there was an argument that what we'd been doing to combat climate change was actually starting to have an effect. Obviously, when we got that 2019 data point in, that was kind of put to bed. But it's interesting going forwards because we've got this that we can look at many different areas on the globe. So another interesting question that came out of that climate community was whether it was change points that we were seeing or whether it was just a long memory process. And so we also kind of extended that work that we'd done previously where we were looking at the different types of models to now include a decision between, is it a change point process or is it a long memory process? So long memory processes and change point processes, if you just look at the, say, the autocorrelation function of a change point process, but ignoring the time dynamics, then it can look very, very, very similar to a long memory process due to just the autocorrelation that's induced by the change point locations over time. It puts in very high lag dependencies, and that can make it look like it could be a long memory process. So there are a lot of people in the climate community that were kind of saying, well, with kind of the dynamics that are going on in these large scale climate systems, that actually it should be a long memory process. And so the top plot there shows us the results of that analysis across individual locations. We treated all of these locations as independent and just ran individual set analyses each. And what you can kind of see is there's a clear pattern there. Within the ocean, in the middle of the plot there, you can see that there's a lot of color going on. And the blue says it's a change point process, and the kind of yellow, orange, red say it's a long memory process. And it's much harder to distinguish a long memory process than it is to say that there's a change point process. So a lot of those blue that you kind of see in the ocean are more kind of borderline measurements, that kind of light blue structure, which says that we're not sure really between whether it's a change point process or a long memory process. So we're going to favor a change point process because you need more evidence for a long memory process. So what you can clearly see there is that basically over the ocean, you're looking more at long memory, whereas over land, you're looking more at change point processes. If you drill that down further and over the change point locations, look at the number of change points, and then again you clearly kind of get a pattern here. So the change point processes that are within the ocean tend to have 0 or 1 change points, whereas a lot of the change points over land, a lot of the change point processes over land tend to have much higher numbers of change points. That's kind of getting onto the green, orange, and pink colours. So this kind of shows that the change point processes, when you're applying them to lots of data in an automatic way, can actually give you some insights spatially as well. But then you might kind of say to me, okay, well, Rebecca, maybe you should be doing a spatial analysis here rather than just looking at these locations individually and then mapping the results. So I'm now going to start to talk a little bit about multivariate data. So when we have multivariate data, as we kind of have in this scenario here, one of the key things that you're kind of looking for is how can I actually reduce that dimension of my multivariate data to be able to handle it more appropriately. So there's a lot of methods like PCA methods and other dimension reduction techniques that are used in the multivariate community in statistics. And within the change point community, a lot of these processes or a lot of these techniques reduce the dimensionality of your data set from, say, p-dimensional down to 1 dimension. Okay, they're typically looking for mean changes, and so they kind of summarize the whole data down into 1 dimension. Okay, which is basically characterizing some form of the mean of the distribution. I say some form of because it's not just taking kind of a straight mean across your dimensions to look at that. And so what we did was we kind of looked at it and say, well, if we were looking at this, I'm not just interested in mean changes, I'm interested in other types of changes as well. So if I'm only interested in one type of change, then I can get my dimension reduction technique to kind of target that specific type of change, which will mean that I can take a p-dimensional down to 1 dimensional but be targeted at the type of change that I'm looking for. But what if I'm interested in more than one type of change? In a lot of the data sets I've shown you so far, you've got autocorrelation, you've got means structures, you've got variance changes going on. And so collapsing all of that down to 1 dimension just seems like I'm losing too much information. So what we did was we kind of looked at a health example, which is around genomics, and we're looking at, well, could changes in the genetic information across the genome give us some kind of hints as to genetic components to diseases? Okay, and so in doing that, when you're looking across the genome, you have mean and variance changes, because essentially you're looking at counts of different combinations of the core components of DNA. Okay, so because you've got both that mean and the variance change, you need to have something that can kind of quantify both of these aspects. So what we did was we kind of took a genomic point of view and said, okay, well, if we're looking at from this is a 2D representation here, if we're looking at a mean change, what does that mean from a geometric point of view? What that means is that my cloud of points in whatever dimension I'm looking in has a shift. Okay, so that's kind of going from the black points here to the blue points. We're taking, this is a 2-dimensional example, you're taking the mean of those two, and if the mean of the x changes, x1 on the x-axis changes, then I'm going to shift sideways. If the mean of x2 changes, I'm going to shift up and down. We're kind of all used to that. So if I have a time series where I have one change point, 2 different distributions, then going from the black to the blue will indicate the change in mean in both of those x1 and x2 here. And if I have a change in variance, essentially I'm going from the black points to the green points where they're becoming more spread out. And so how would we be able to detect that in potentially p-dimensional space where we can't visualize it as we can here? And the way that you can kind of look at these changes is you can look at, well, what is the distance from a fixed point Here I've used 0, 0 because I've rescaled the data into the top quadrant. So if I look from a fixed point 0, 0 and look at the distance of every point to my fixed point, then I can get that the change from the black to the blue, that mean shift, just by looking at a change in those distances. And it doesn't matter if the mean is only shifting in one variable or it's shifting in lots of variables, I will still get that mean shift change, provided that that change in distance is large enough. And then if I'm going for the green points here, then I need to look at the angle. So it's not only the distance here, it's the angle from my fixed point to each of these different data points. And so if my angles are if the mean, when I'm looking at the angles, if I'm looking at the angles of all of the black points, they're all going to be very similar. So they're all going to have a similar mean structure. And if I'm looking at the angles to the green points, I'm going to have lots of different examples, lots of different angles here. And so I will get a larger set of data. If I'm looking at the angles from the black points to the blue points, there may be some shift there, but they're going to be very similar because the cloud has just shifted. Obviously, if I only shifted in one axis there, then my angles would also be shifted as well. So that angle measurement really gives us quite a lot of information. So if we do this on genomic markers, for example, then instead of using just one transformation, which would target the mean structure, we can use two transformations, the angle and the distance, which are the two blue and red at the top. And this is a portion of the data that I'm showing you here. And what this kind of is demonstrating is that when we have periods kind of around 500 there, where we don't actually detect change points, but you can see in the very bottom graph, there's quite a lot of changes in that data. But what we're saying is that those changes are not large enough when we look at across the whole data set. So it's not producing a large enough shift. So you can look in both the angle and the distance at the top, and that's not large enough. So basically, when you're looking across the whole data set, the cumulative effect of all the changes that you're looking at across all the data points is not large enough to signify a change there. So that's helpful in genomics because it means that some individual variations that are not attributed to disease are not going to show up in the change point locations. Okay. So if we kind of go on further and take that a step further, you might say, okay, well, actually, I want to know which people which genomes have are actually signifying where the change point is. So that's a more challenging problem, and one that hasn't really been tackled in the field. So we have one paper that's kind of currently in submission that looks at this, but it's not really something that's been tackled. People either assume that a large portion or a small portion of the variables will change and kind of have that difference there. So what we've looked at here is where we're calling it subset multivariate change point methodology, and this will both identify where the change points are, but also which variables are changing. And if you're looking at p dimensions, you can clearly imagine this is going to be a really challenging problem, more so than the 2 to the n-1 that we were talking about in the original setting. So this large set of changes here, what we're basically looking at is we have many different patients, and we want to know which areas should we be looking at for potentially having investigation to see if that portion of the genome is a potential cause or gets corrupted and results in this disease. So the existing technologies, like I kind of mentioned on the previous slide, can give you an indication, but that doesn't tell you which patients. So that could just be that that's changing in all the population, okay? So if you do a mix between diseased and non-diseased patients within a data set, then you can have a look at, well, which are changing in the majority of patients and which are changing in the majority of the population. So here we found only 10 changes that were present in more than 60% of the patients, whereas all of the kind of what I would call competitors, where they can't identify which variables are changing, detected over 50. So you can clearly see now from an investigation point of view, now I only have 10 that are probably the most common for me to target with potential therapies, whereas there was over 50 previously that I would have to look at. So kind of moving on to kind of more cutting edge work here now. So I kind of mentioned previously about model selection. Okay, and model selection is a huge issue in changepoint problems. And one of the problems with it is that when you are viewing data over time, in the kind of PELT paradigm that I was talking about previously, as you're looking at the data sequentially, you're assuming that these segments that you're getting are independent from one another. So if you have kind of a reoccurring change point pattern, maybe a yearly pattern or something like that, then every year you will kind of have a different set of parameters. And that's not really ideal, because we want to be parsimonious in our model building, and really we want to be able to say that they're the same type of processes. So I could look at maybe a hidden Markov model structure to kind of look at that, but then a lot of the estimation techniques there, I'm going back to my approximate setting, and I'm not really comfortable with doing that. So a recent paper that's been published looks at passive monitoring of patients at home. So clearly with the COVID-19 pandemic, this is kind of exacerbated. You didn't want people traveling to hospital if they didn't need to, but then at the same time, you wanted to be able to monitor their diseases remotely, so that you can actually intervene if you did have to, if it was necessary. So this kind of project has been going on for a very long time, even prior to COVID, for kind of monitoring people in their home, because a lot of the elderly population actually, in the UK at least, leave their health issues until it's too late. And then that means that they need to be hospitalized, when if we would have caught it early, even just something like a urinary tract infection results in hospitalization for 2 weeks, which has lots of negative outcomes going on after it. Whereas if we would have caught it early, then we could have just given a little bit of over-the-counter medication, and that would have fixed it without hospitalization at all. So what we're seeking to do here is to passively monitor people. These are elderly people. They're not going to wear Fitbits. They're not going to adhere to any programs such as that. So we want to do some passive monitoring. So just things like motion sensors and door sensors, and maybe some plug sensors in the house. And so a lot of elderly people tend to have a very regular routine, some more than others. And so what I'm showing here is kind of the 1 day in the graph, where the change points are the different levels of activity. And then in the circular plot that I've got on the left, you're looking at, well, what does that look like over different days of the week? And you can clearly see that there's kind of some kind of day of the week effect, especially with weekend versus weekday, which is interesting because that's not in all of the patterns. So this is kind of using circular views to get that kind of daily pattern repeating over time. And then that daily pattern is whilst there's change points within the day, to estimate the kind of changes within the day that indicate different periods of activity. We can also have changes over time as well. That's a paper that's currently under review. So the last thing that I kind of want to talk about today is around sensitivity. Okay, so I've kind of talked about getting the change points and how many change points there are and where they are, but we haven't really looked at in the change point community yet about how the data that we've observed influence the change point locations. So the well-log data is the top process there, which has lots of outliers in it. It also has lots of or some autocorrelation in there as well, but it also has some changes in mean behavior as you go through different strata of the rock. Okay, so if, for example, I delete one observation 685, then what happens in the highlighted segment is that I actually get rid of 4 change points. So just by deleting one observation, I go from having 4 change points there to having none. Now, to me, that is a huge change, a huge sensitivity issue to kind of say to me, well, are those change points really there? Or is it just a function of the data that I've observed? Okay. If I do something the opposite end, so rather than deleting a data point, I make a data point an outlier, which I've done to observation 326 there in the bottom plot. What I do is that change point that's just before 400 in the top 2 plots disappears completely. So that's again telling me that just by modifying one observation, I can get rid of a change point that doesn't seem to be an erroneous or potentially erroneous change point there. So this is something that we've been looking at very recently. The paper's just been accepted in Journal of Computational and Graphical Statistics. And we're coming up with some stability measures there where we can actually label change points as stable, which means that they don't change under these variations, unstable, which means that they do change in some way, or they're an outlier observation. So we can kind of do some of this labeling. Not only can we label these, but we can tell you what the effects are as well. So here, the boxes, the height and the length of these boxes tell you something about what happens in the change point. I haven't got time to go into what, but not only can I tell you which change points are stable, I can show you how stable they are. So clearly here, the very thin lines are going to be, yes, they are unstable, but they're not unstable in the same way that some of the large boxes are. Okay. So just to kind of come to an end so that we've got time for some questions. So I've talked kind of about 2 open problems there around kind of sensitivity and also more complex model structures in the kind of circular data perspective. There's clearly other open problems around autocorrelation. There's tons of issues still there, despite having done more work on that in recent years across the field. Multivariate data is still an issue because even that subset approach that I was talking about, it's still not computationally efficient. There's a lot of work that can be done there to kind of improve the computational cost of multivariate data, as well as looking at more complex structures within multivariate data, talking about like spatiotemporal data and things like that. Model complexity is still an issue, so the kind of circular perspective that I kind of touched on earlier is starting to kind of increase some of that model complexity that we have within change point problems, but that comes with a cost as well, because increasing model complexity increases the time for that. And online changes as well. So when you're looking at online stuff, a lot of that's come to the fore with the pandemic of having to make decisions in an online manner, but there are many different applications of online change points, including in kind of like security and defense issues applications. So just to summarize, so change points occur in most data. Whether you're happy to look for them or not is another question. They may just be a nuisance, but detecting and documenting them does improve the analysis. I've got one paper that I've put in the references that kind of looks at, well, where should change point detection be within your pipeline? Should it be a pre-processing step? Should it be within your modeling step? Should it be a post hoc analysis? And where you do the change point detection matters in terms of the accuracy of your analysis, depending on the question that you're wanting to answer. So multivariate online big data mostly isn't a problem, but there are still plenty of open problems in the field. And I've kind of given you a few different applications that I've worked on there in a very overarching point of view, but generally I enjoy real life messy data because it's working with that real data and seeing the problems in that field that actually sparks my next research challenge that I'm looking at. So thank you very much. I've got lots of papers links that are in the version that I've sent to Mohammed, so that you can have a look at that if you would like.
Okay, thanks very much, Rebecca. Any questions for Rebecca?
I think there's one from Kate.
Yep.
Errors that aren't normal. That is a good question. I have kind of spoken more about model building from a kind of parametric point of view here. So if they're not normal in the sense that they are heavy-tailed, then actually the PELT algorithm is more robust to that than as a search algorithm than the other approximate algorithms, even with the same kind of test statistic that you're looking at, which is interesting as a kind of dynamic. You can include non-normal error structures. It really depends on what assumptions you're willing to make. If you can fit the model to an individual segment, then you can fit a change point model with that model as well. So if you've got a model that you're happy to work with that has a more flexible error structure, as long as you can fit that to a single segment of data, you can generalize that across. So that kind of comes with that. And can you use these methods to look at change points, emergence of climate change in rainfall data? Yep. So if you kind of look on my website, I've got which kind of is at the top there. I've got a recent paper that's looking at changes in rainfall, actually. We're looking at whether the type of rain that we're seeing is changing over time, as along with the kind of climate change aspect. So within the UK, at least, there's if you're just looking at the amount of rainfall that we're seeing, we're not actually seeing much change over time. The difference that we're getting is we're getting longer, shorter stints, heavier stints. So that's causing a lot of localized flooding. And this is because of the type of rain that we're seeing. So we're kind of looking at westerlies, is what we call it in the UK. But basically the different type of rain that you're getting will change the type of problem you're looking at. And we've seen that there has been a change in the type of rain that we're getting. But the problem is that the type of rain that we're getting does change over time naturally. So again, it's kind of this kind of hierarchical approach where you're kind of saying, well, okay, there's a pattern for how these change points in types of rainfall occur naturally over the, you can look at historical data for that. And then, well, let's look at this century and say, well, has there been a change in the pattern of those changes, which is where we're kind of getting into increased model complexity there. And then, so David says every application is different. Can you give us a sense of what can be at stake in change point detection scenarios? Okay, yes, I can, David. So one, a bunch of different things. So if we want to kind of look at security scenarios, so a lot of change point detection is used in detecting intrusions within computer networks and things. And so that is obviously a very serious scenario. If you don't detect an intrusion quickly enough or put mitigations in place quickly enough, then you've potentially lost billions of pounds, as we can kind of see with a lot of these ransomware attacks and other things like that. So there's potential there where the stakes are kind of high from a monetary point of view and a type of life point of view. We looked at, in COVID-19, there was change point detection going on to kind of look at, well, are our strategies making a difference, or should we be trying something else? And so that was having to be done in real time, and that's kind of more of a life issue. A lot of lives were saved if actions were taken in a timely manner from that point of view. Flooding is another one of those where we have some change point detection kind of looking, am I going away from what I would expect to be seeing? So this is kind of in the online sense, and I've put a recent online paper with some code in the here. The online paper there, I gave a talk recently that's been recorded as well, if you want to have a look at that, where we're kind of saying, well, I can look at what I'm going forwards and say, is what I'm seeing now different from what I expected to see? If the answer is yes, then maybe something is going on and I need to take action. In Lancaster, we had a big Storm Desmond flood, and if we would have been, we've kind of done replications of the scenario with some change point detection in place that wasn't in place at the time. And if it was, then we would have been able to actually give an indication about 6 hours earlier that the flooding was going to take place, and that could have allowed some evasive action to be taken. So there's lots of scenarios there where the stake of detecting these changes can potentially be quite high. Okay, what's the size of your model space in the model choice problem? Has this influenced the approach you used? Good question, Lawrence. So the size of the model choice that we used in the climate example. So let me go back to this one here. So here we were looking at mean no change, mean change, mean and autocorrelation no change, but with several different lags. So that's kind of increasing the space there. I think for this paper, we looked at 12 different model structures. So that's kind of the size of the model space that we were working on here. When we added in the long memory, that was 13, counting the fact that the long memory process was optimized across an additional model space there. But the kind of broad model spaces that we were looking at was 13, but obviously within each of those is an optimization procedure itself. So that kind of takes that. Has it influenced the type of approach you use? Yes. So for that one, we could do kind of an exhaustive search across the different model structures. But because of how fast the change point approaches are. So if we didn't have the Pell algorithm, we wouldn't have been able to do an exhaustive search there. But we were allowed to. So that whole analysis there for all of those locations took a couple of hours. So it's not, heavy computational time-wise. The problems that we're kind of getting into now, so we've got some soil applications that we're looking at for looking at changes in the health of soils over time. And there the model space is increasing drastically because we're including a lot of the process-based models, so non-statistical models there, and kind of the process-based stuff that is used within the soil science sphere. So we are having to take a different strategy to the exhaustive approach that we took here. But yes, thank you.
Okay, thank you very much, Rebecca, for your perfect presentation.